The lesson today is on orbitals and the shapes of the orbitals. If you recall from the last section, we talked at the very end about Niels Bohr and his model of the hydrogen atom. The hydrogen atom worked very well. The model worked very well for just the hydrogen atoms, but not for any other atoms. It's very easy to predict the hydrogen, but we couldn't predict anything else. So the other problem with Bohr's model is that it did not have the correct sort of shape that the electrons travel in. So his model predicted that they traveled in circles. However, that's not really the case. So this should give us a little bit better picture of what's really going on with the electrons in an atom. So to begin with, thinking back to last section, we talked about the n values being the levels inside of the atom, the energy levels inside of the atom. Well, n is actually called the principal quantum number. Okay, n is called the principal quantum number. That means that it indicates the relative size and energy of atomic orbitals. So n tells you how big the orbitals are and the energy in that orbital. Okay. As n goes up, the orbital becomes larger, and the electron spends more time further away from the nucleus. So for instance, down below, if we draw this kind of like this, okay, as we're moving away from, if we put the nucleus as this red dot down here at the bottom, okay, as we move away, we have n equals 1. Whoops, don't want that. Let's do a little bit smaller. There we go. So we have the n equals 1 level there, the n equals 2 level here, n equals 3, and you can go all the way out to n equals 7, okay, technically for hydrogen atoms. But the further out you go, the more energy associated with that. So as your n increases, the orbital becomes larger, you're moving further away, and those electrons have more energy in them. So n specifies the atom's major energy level. How far out are these electrons? That's the major energy level. Again, that's called the principal quantum number. The lowest level is n equals 1. That's called the ground state. Okay, and like I said just a minute ago, theoretically we could go all the way out to n equals 7. For each n value, there are a set number of sublevels within that value. So for n equals 1, this is pretty straightforward. It has one sublevel to it. For n equals 2, that has 2 sublevels to it. N equals 3 has 3 sublevels. All the way out, n equals 7 would have 7 different sublevels in it. And if you kind of want to think of it like as if the center of the auditorium here, the stage, was like the nucleus of the atom, and as you move away from it, there are more sublevels. So this first one would just have one sublevel. The second one would be split up into 2. The third one split up into 3, so on and so forth. Kind of like what you see over here. All right, it makes it easier to move around. All right, so what's happening over here in the theater, that's what's happening. Same kind of idea is happening within the atom. Okay, so these are sublevels within the principal quantum numbers. So these sublevels are labeled as S, P, D, or F according to the shape. So they are letters, S, P, D, and F. Those indicate the shape of the orbital. So the sublevel, okay, think of the sublevel. When you see the sublevel, think of the shape. Think of those as the shape of the orbitals. Okay. The easy ones, S orbitals, are spherical shaped. It's not because this letter S means spherical. They actually come from German words. We just took the first letter of them rather than learning the German of it. So we had S, P, D, and F. So S orbitals are spherical. P orbitals are dumbbell-shaped. We'll see what those look like. They're kind of elongated, sort of elongated figure eights, a little bit bigger on the ends there than I drew. And then the D and F orbitals have more than one possible shape. They get a little bit more complicated. Basically, the more electrons you got in something, the more complicated the orbitals have to be to account for all of that space. Try to get them packed in there as neatly as possible. So at the n equals 1 level, the principal quantum number, you have one sublevel. The only available sublevel to you at this is the S sublevel. Electrons in this sublevel are designated as 1s. The 1 is coming from the principal quantum number up here, the n equals 1. The S is coming from the shape of that orbital. Okay, so this is in the ground state. Remember, the n equals 1 is the ground state. Okay, there's only one sublevel available here, which is an S, and that's referred to as 1s. So electrons that make up, say, a hydrogen atom or a helium atom, okay, those are in the 1s level if they're at ground states. Okay, those are spherical in shape. If you look at an n equals 2 sublevel, it's got two shapes. You have S and P shapes. Okay, so if the principal quantum number is 2, you've got two sublevels, S and P. Electrons at this level are designated as 2s and 2p. And again, the 2 is coming from the principal quantum number, and then the letters come from the shapes of the orbitals available at that principal quantum number. So we've got S and P available when n equals 2. The 2s is spherical, and the 2p's are dumbbell-shaped. One thing of note here is that up top there is one orbital when it comes to S shapes. Okay, there's just one orbital there. So here there's just one 2s orbital. That's it. There's only one of them. But note that the P here, the P shape, actually has 3 orbitals to it. Okay, so it has 3 orbitals. So note the difference there. So up top, we have a total of 1 orbital. There's only one orbital at the beginning, that 1s. Here, we've got one orbital that is 2s. If n equals 2, you got a 2s orbital, and you have 3 2p orbitals. Okay, that gives you a total for the n equals 2 level of 4 orbitals. Okay, you got 4 orbitals total. So that is one thing to note. Okay. So what do these things actually look like? Well, we said that the S ones are spherical shaped. Okay, in this picture right here, the only difference between this one and this one, the 1s and the 2s, is the size. Okay, a 1s orbital is going to be closer to, if you imagine the middle of this thing once again being the nucleus, okay, imagine that being the nucleus of each of these atoms, then the 1s should be closer to the nucleus, which it is here. Okay, the 2s is going to be further away. Okay, the 2s orbital is further out. That's the only difference between the two. Okay, and you could superimpose this image underneath here, and then you'd have 1s electrons going underneath. And if you have enough electrons in the atom, then the 2s ones are going to go around like that. And for the p-shaped orbitals, they are dumbbell-shaped. These lie along the axes. So here, this one lies along the x-axis. We label that the px orbital. Here, this one lies along the y-axis. We label that the py orbital. And this one lies along the z-axis. That is the pz orbital. In reality, they are not in separate planes like this, okay? They are all put together, not separate planes, but separate axes. These are all put together. And if you take the two on the outside and bring them here in the middle, okay, I'm going to try to draw this. We'll see how well it works. Okay, if we draw the one that's on the z orbital here, and draw the one that's along the x-axis, okay, what you'll note is that they shouldn't have any overlap. They should be completely free of each other. They shouldn't have overlap. The reason for that is this space is filled with electrons. Remember, the space is filled with electrons. And so what ends up happening is if you've got a bunch of negative charge all together, like charges tend to repel. So if you had any crossover here, you'd have electron-electron repulsion. Those electrons are going to push each other apart. So what the atoms do is they maximize the space in between each of these orbitals. They try to give the electrons the most amount of space to move around. That's what's going on here. Another important note here is that the orbitals are not paths. Okay, electrons do not travel in figure-8 paths like this. That's not how this works. Okay, they don't follow along the axis like this. They don't go back and forth like this. Okay, what are the orbitals then? Well, the orbitals are strictly this. Okay, the orbitals are regions with a 90% likelihood of finding an electron, So what does that mean? These are not paths. They don't travel around like this. All that these blue regions here represent are that an electron that's in a pz orbital, 90% of the time it falls somewhere in here. Okay, we don't know its path. We just know that it's a 90% likelihood falling within here. It could, for instance, if it was in a pz orbital, lie outside of this, roughly 10% of the time. Okay, 90% of the time, though, they are inside of this blue region. How do we know this? Well, there are some classes in college you can take if you go on to study chemistry that explain why the shapes are what they are. And you can actually set the probabilities even higher. However, you start getting closer and closer to 100. These get bigger and bigger and bigger to the point at which they finally fill up the entire grid, which is not very helpful. So with a 90% likelihood, you can kind of see the paths that these things must be taking. And this is true of every orbital. This is true of S, this is true of P, this is true of D, this is true of F orbitals. Okay, I'm just writing it here on the P orbitals, but it's really true on any of them. They're not actually paths. So if you go back to the previous slide with that sphere, they're not going around in circles or around the outside of the sphere. They're just found somewhere inside of that region. Okay, that's strictly what that means. Here we have D orbitals. These are referred to as cloverleaf shapes. These are referred to as cloverleaf shapes. So you can kind of see that here. Each one's got 4 lobes to it. And they lie in a plane. This first one lies in the XY plane. You got 4 of them, and it lays flat on the XY plane. So imagine, if you will, going back into the screen. We label that one the DXY orbital. This one right here lies on the XZ plane. Okay, so again, this is as if it were going in and out of the screen, coming out towards you like that. So that would be a DXZ orbital. Here you have a DYZ orbital that's on the YZ plane. Okay, once again, going in and out of the screen. Here, this one is laying flat with the screen. It's in between 2 of the planes. It's between the X and the Y planes. Okay, this one's sitting straight up and down, flat on the screen. And then lastly, you got the shape here that once again looks like a lobe, and you kind of got this donut feature there in the middle that where it also could be found. Okay, so these are the D orbitals. These are D orbitals. You're only going to see these when you have n equals 3, because you can't have your three sublevels with n equals 3 are S, P, and D. Okay, you have S, P, and now D. So if you have n equals 3, you could have theoretically a 3s orbital. You could have 3 p orbitals. You could have a 3px. You could have a 3py. You could have a 3pz. Okay, and then you could have, if you count them up here, 5 total d orbitals. Okay, and we're not going to take the time to write them all out, but you could have 5 of these. 5 of these. Okay. We're not going to write out every single one of these, but you'd have XY, XZ, YZ between the 2 planes there, and then you have one sitting along the Z-axis. So those are cloverleaf. Those are when you get n equals 3. So in a hydrogen atom, where are the electrons located? Well, they can only occupy 1 orbital. Since it's a hydrogen atom, you only have 1 electron. There's only 1 electron here. So where is it? Well, it can only occupy 1 orbital at a time. So if the hydrogen atom is in a ground state, okay, if it's in a ground state, we haven't given it any energy, that means n equals 1. If n equals 1, the only available orbital is an S-shaped orbital, so it is spherical. Okay. If we give that hydrogen atom energy, okay, if we give the electron energy, it's going to move up. We talked about transitioning between the n values. Okay, it's going to move up. It can occupy any of the vacant orbitals above it. It could occupy 2s, 2p, 3s, 3p, 3d, any of those above it, it could occupy. Okay, it'll go into any of those orbitals above it, and then if it jumps back down, that's when you see the emission, right? That's when you see the photons being emitted. Well, this isn't important for hydrogen because hydrogen only has 1 electron. Okay. But there is a maximum of 2 electrons per orbital. You can't fit any more than 2 electrons per orbital. Reason being is that if you've got more than 2, you're going to have too much charge trying to repel each other in a very little amount of space. Okay? So these, if you had 3 in there, they're going to push each other apart. Okay, they don't want to stick around next to each other. They're going to move away from each other. So you can only have up to 2 electrons per orbital. So that one s orbital can only hold up to 2, which would be hydrogen, and then helium would have a second one if it was a helium atom. This last chart right here is very helpful, kind of putting everything together. If you've got n equals 1, there's only one type of orbital present. N equals 2, you've got s and p. N equals 3, you've got s, p, d. If you have n equals 4, we didn't talk about that one, but you can have s, p, d, and f. If you're interested, you could look up what an f orbital looks like online. Okay, they get kind of crazy. We're not going to ask you to ever draw one of those, but you can go look those up. They're very interestingly shaped. So number of orbitals related to sublevel. So right here, with the first one, if n equals 1, we only had one s. That was a total of 1. Okay, if you had n equals 2, you had one s orbital. You had 3 p orbitals, those are the dumbbell-shaped ones, for a grand total of 4. If you have n equals 3, the sublevels are s, p, and d. Well, the s is always 1, the p always has 3, they're the dumbbell-shaped, and d always has 5 orbitals. Okay, if you add those up, you get a grand total of 9. All right, and the last one here, if you got n equals 4, you have s, p, d, and f. So if you've got that, you've got 1 s orbital, 3 p orbitals, 5 d orbitals, and 7 f orbitals. Like I was saying, these get kind of crazy when you got to account for 7 different orbitals happening. Add those all up, it gets to 16. So a thing to note over here, the total number of orbitals for each n value is simply, when you add them all up, it's n squared. Okay, it comes out to being n squared. So if it's n equals 1, ends up as 1. N equals 2, you got 4 over here. That's the last thing to take away from that.